In this video, you're going to get introduced to the concept of exponential functions. We're going to look at it through an example in the real world, just so that you can see one thing, why is it interesting and why is it important, but also I think because it helps give you a better understanding of what's actually happening here, if we can put some kind of real world context. Imagine that you've got an investment that increases in value by 8% each year. And just to start off with a nice round number, let's say you start with an investment of 500 euros. So after 1 year, that amount of money is going to increase by 8%. If you want to increase something by 8%, that means we need to find 108% of the original value. So we could find the next year's value by multiplying this 500 by a factor of 1.08, right? This is the same as 108%, or an 8% increase. And if we do that calculation, we end up with 540 euros, which is pretty great. 1 year, you didn't really do any work, just have to have a little bit of patience and you earned 40 euros. Now the great thing is, in the next year, in the second year, we get 108% of this new value. So we multiply 540 by 1.08. And we didn't just get 40 euros this time, we got 43 euros and 20 euros cents. So we actually got more extra money this time because we're adding a percentage of a greater amount, right? This original amount is greater than the original 500. So 8% of this is more than 8% of this. And this continues on, which is really the exciting thing about exponential functions. So to find the third year, we multiply by 1.08 again, and we get 629 and 86 cents. This is rounded. It's not exactly that amount, but it's rounded to the nearest cent. And for the fourth year, we would get 680 euros and 24 cents. For the fifth year, we would get 734 euros and 66 cents. Okay, so far, you might notice that this is the same as a geometric sequence. And that's exactly what it is. This is just a geometric sequence. The first term was 500, and the common ratio is 1.08, because to find each following term, we multiply by 1.08. Over and over again, we multiply by this ratio. Okay, so just to make sure this is really crystal clear, we'll write out these multiplications. So at the very beginning, when time is equal to 0, we start with 500. We call that f of 0. Right? F of 1 is the investment value after 1 year, and that's what we got when we multiplied 500 by 1.08. To find the second year, what we did is we multiplied 500 by another 1.08, so we have two factors of 1.08, and you'll see the pattern hopefully is quite clear. The number of times we multiply by 1.08 is equal to the number of years that we've waited for this investment. So if we wanted to write a function for this, instead of just calculating 1 year at a time, our function would have to have repeated multiplication in it. And repeated multiplication is what is meant by an exponent. So that's why we call these things exponential functions, because we are multiplying by the same thing over and over again, which means we are using exponents. And in fact, this is what the function would look like. You'll notice it looks really similar to the formula for geometric sequence, where this is the first term, 500, and this is the common ratio, 1.08. Okay, so for example, if you wanted to know the value after 10 years, all you would need to do is plug in a 10 for x and calculate 1.08 to the power of 10, and then multiply that value by 500. Now, one important thing about exponential functions is that the exponent itself is the x. Okay, so the exponent is the independent variable. Just because something has an exponent doesn't mean that it's an exponential function. So for example, the graph of a parabola, y equals x squared, that has an exponent, but it's not an exponential function because the exponent is not the independent variable. Right? So if you want to identify an exponential function by looking at the equation, got to look for the independent variable to be in the exponent here. If you're just trying to identify exponential growth by looking at the pattern, what you need to do is find a common ratio. If you can find common ratio, then that means that we're looking at an exponential function. So let's take a look at this on a graph. So here, this green line here is a graph of the value of our investment. The x-axis is time in number of years, and the y-axis is value in euros. So not very much surprising here. It's going up, which you expect, and what's nice about this is that it's not linear, it's actually curved upward. So you can see there's a slight curve in that graph, which means not only is the investment increasing, but it's increasing at an increasing rate. Last thing I want to show you is what happens when you zoom out of a function like this. So if you zoom out here, and look at what's happened now, you can see the upward curve is getting steeper as we go here. So if you think about this in terms of slope, you can think that the slope of that line is increasing, and I shouldn't be calling it a line, I should be calling it a curve. So the slope of this curve is increasing as we move to the right, as the number of years increase. What that means is you're gaining more and more money each additional year. Let's zoom out a little bit further. Now this is where things are getting really exciting. You can see that if you have the patience to wait 30 years, that investment that was originally 500 euros is now all the way up here, just over 5,000 euros. So its value has increased by a factor of 10. Now to really make my point clear, let's see what happens after 100 years. I'm going to zoom out even further here. So look at this. It's increasing so steeply that after about 50 years, we can't even see what the value is on this graph. So now I need to change the scale on the y-axis because this curve is growing so steeply. Okay, now check this out. After 100 years, if you're patient enough to wait that long for your investment, you'll find that the function has this value here. And if you trace that all the way over to the y-axis, this is more than 1 million euros. It's 1,100,000 euros, it looks like. So we went from 5,000 euros to over 1 million euros. This is what's really, really powerful about exponential growth. And we're going to keep coming back to this concept throughout the unit, that the growth doesn't seem very big early on in the graph. Down here, the graph looks quite flat. But as we go further and further, the growth gets greater and greater and greater, and the numbers get almost out of control.